Hello students, today we'll be studying the basic concept of energy expenditure and units of energy. Let's begin with the introduction. Energy is that force or power that enables our body to carry on its life-sustaining activities. Metabolism is a total of all those chemical processes in the body in which substances initially in food are changed to other substances. The energy that the human body requires to maintain its organic and vital functions is obtained by the oxidation of macronutrients from food. Energy expenditure can be considered a process of energy production from combustion of energy substrates like carbohydrates, lipids, proteins, and alcohol, in which there is an oxygen consumption and carbon dioxide production. Part of this chemical energy is lost as heat and in urine, and the remaining energy is stored in high-energy molecules like adenosine triphosphates or ATPs. Let's look at energy intake and expenditure. A regular supply of dietary energy is essential for life and is required to fuel many different body processes. These include keeping the heart beating and organs functioning, maintenance of body temperature, muscle contraction and growth. However, daily energy requirements vary widely from one individual to the next. This is due to factors such as sex, body size, body weight, climate, and physical activity levels. So energy is obtained from the food and drink we consume by oxidation of carbohydrate, fat, protein, and alcohol known as macronutrients. The amount of energy that each of these macronutrients provides varies. Fat is the most energy-dense nutrient and provides about 9 kilocalories, that is 37 kilojoules per gram. Alcohol is the second most energy-dense nutrient, providing 7 kilocalories or 29 kilojoules per gram. Protein provides 4 kilocalories or 17 kilojoules per gram, while carbohydrate, like starch and sugars, is the least energy-dense nutrient, providing just 3.75 kilocalories or 16 kilojoules per gram. Application of these factors to the food and drink consumed enables energy intake to be estimated. Let's look at the units of energy. Energy intake is often measured in joules, denoted by J, or kilojoules, as in kJ. But many people are more familiar with calories, as in kilocal. The calorie is defined as the amount of heat required at a pressure of 1 standard atmosphere to raise a temperature of 1 gram of water through 1 degree Celsius. Since 1925, this calorie has been defined in terms of the joule. The net definition since 1948 being that 1 calorie is equal to approximately 4.2 joules. So 1 kilojoule equals to 1000 joules and 1 megajoule equals to 1 million joules. 1 kilocalorie equals to 1000 calories. To convert from one unit to another, 1 kilocalorie equals to 4.184 kilojoules. So a 1000 kilocalorie diet provides 4.184 megajoules or 4184 kilojoules. So 1 megajoule equals to 239 kilocalories. Now let's study the components of the total energy expenditure. Energy expenditure is the sum of the basal metabolic rate, denoted by BMR, the amount of energy expended while at rest at a neutral temperature and in the fasting state. the thermic effect of food, denoted by TEF, otherwise known as the dietary induced thermogenesis, and the energy expended in the movement of all types. So, total energy expenditure, TEE, is the energy required by the organism daily, and it is determined by the sum of the three components. Number 1, basal energy expenditure, BEE, or basal metabolic rate, BMR. Second, diet-induced thermogenesis, DIT, or thermic effect of food, TEF. And the third, energy expended during physical activity, denoted by BA. Let's look at basal energy expenditure, BEE. The BEE is the amount of calories spent per minute or per hour, which can be extrapolated to 24 hours. It also represents the minimal energy required for the maintenance of the body's vital functions. The BEE is one of the most important physiological information in clinical and epidemiological nutritional studies, since it is used to determine the energy requirement of an individual or population. The BEE contributes for 60% to 70% of the daily energy requirement for most sedentary individuals and nearly 50% for those physically active. Its determination is useful to compare the energy metabolism between individuals. This component of TEE must be measured under standardized ambient conditions such as controlled temperature and humidity. The subject must be at complete rest after at least 8 hours of sleep and after a 12 to 14-hour overnight fast. Also, during the measurement, subject must be kept fully awake, laid down quietly, completely relaxed and breathing normally. The value obtained is extrapolated to the 24 hours of the day and therefore is referred to the basal with minimal influence of DIT and BA in the TEE. However, the measurement of BEE requires the subject to sleep overnight in the metabolic unit. Thus, instead of BEE, the resting energy expenditure, REE, is usually measured since there is little difference between them. Many individual factors may affect BEE, such as ethnicity, weight, lean body mass, age, smoking habits, physical activity, diet, menstrual period, and fasting. The room's conditions like temperature, noise, and time of resting, and technical factors related to the equipment's use may also affect the BEE measurement. Other factors which may also affect BEE at different levels would be thyroid and sexual hormones, growth, fever, sleep, metabolic stress, disease, and others. Resting energy expenditure, REE. The REE is a component of EE, which can be 3 to 10% higher than BEE due to DIT and the influence of most recent PA or physical activity. The procedures for measuring REE are very similar to those for BEE. The greatest difference between them is that in REE estimation, the subjects have to be resting and fasting for shorter time, at least 30-minute rest and 3-hour fasting. Now let's study the thermic effect of food, DEF, or diet-induced thermogenesis, DIT. Diet-induced thermogenesis, or DIT, is the energy expenditure component related to the energy required for digestion, absorption, usage, and storage of nutrients after food intake. The DIT represents 5% to 15% of the TEE, or total energy expenditure, and plays an important role in the regulation of energy balance and of body weight. The thermic effect of food on TEE varies according to the type of macronutrient intake, that is 0 to 3% of lipids, 5 to 10% for carbohydrates, and 20 to 30% for proteins. DIT is higher for proteins because their synthesis requires at least 4 energy phosphate bonds or ATP per amino acid incorporated into a protein molecule, with a dispense of 0.75 kilocalories per gram of the synthesized protein, and the high metabolic cost of ureogenesis and gluconeogenesis. The energy expenditure increases significantly after a meal. So the thermic effect of food is mainly due to the energy cost of nutrient absorption and storage. The total thermic effect of food over 24 hours represents the 10% of the total energy expenditure in sedentary subjects. The thermic effect of nutrients mainly depends on the energy costs of processing and or storing the nutrient. Glucose-induced thermogenesis mainly results from the cost of glycogen synthesis and substrate cycling. Glucose storage, as glycogen requires 2 molecules of ATP per molecule of glucose. In comparison with the 38 ATP molecules produced on complete oxidation of glucose, the energy cost of glucose storage as glycogen corresponds to 5% or 2 by 38 of the energy content of glucose stored. Cycling of glucose to glucose 6-phosphate and back to glucose to fructose 1,6-diphosphate and back to glucose 5-phosphate or to lactate and back to glucose occurs at variable rates and is an energy requiring process that may increase the thermic effect of carbohydrates. The thermic effect of dietary fat is very small. An increase of 2% of its energy content has been described during infusion of an emulsion of triglyceride. This slight increase in energy expenditure is explained by the ATP consumption in the process of free fatty acid reesterification to triglyceride. As a consequence, the dietary energy of fat is used very efficiently. The thermic effect of proteins is the highest of all nutrients. So that is 20 to 30% of the energy content of proteins. Ingested proteins are degraded in the gut into amino acids. After absorption, amino acids are deaminated, their amino group transferred to urea, and their carbon skeleton converted to glucose. These biochemical processes require the consumption of energy, accounting to approximately 25% of the energy content of amino acids. The second pathway of amino acid metabolism is protein synthesis. The energy expended for the synthesis of the peptide bonds also represents approximately 25% of the energy content of amino acids. Therefore, irrespective of their metabolic pathway, the thermogenesis induced after absorption of amino acids represents approximately 25% of their energy content. There are some factors that may influence and modulate DIT, such as the stimulus to the autonomic nervous system, hormones, diet palatability, physical activity, PA, body composition, adiposity, and diet composition. Now, let's study the third component of energy expenditure, which is physical activity. Physical activity should be an important component of our daily energy expenditure. Many different types of activity contribute to our total physical activity, all of which form an integral part of everyday life. Total physical activity includes occupational activity, household chores, caregiving, leisure time activity, transport like walking or cycling to work, and sport. Physical activity can further be categorized in terms of the frequency, duration, and intensity of the activity. We can also say that physical activity, PA, represents the thermic effect of any movement that exceeds BEE, which have a great variability inter- and intra-individual. In active individuals, the energy required for physical activity can correspond as 1 to 2 times the basal energy expenditure, BEE, while in sedentary individuals, it can represent less than half of the BEE. Energy expenditure estimation. Commonly used methods to estimate energy needs are: number 1, predictive equations using anthropometric data. This method of estimating BMR poses the least subject burden, is low in cost, and relatively fair in precision when compared to the measurements from calorimetry. Out of the various equations validated, the Mifflin equation to predict energy expenditure was found to be the most accurate predictor of energy expenditure of individuals compared to direct calorimetry. The gender-specific Mifflin equations are as follows. For males, REE equals to 10 into weight in kgs plus 6.25 into height in centimeter minus 5 into age in years plus 5. For females, REE equals to 10 into weight in kg plus 6.25 into height in centimeters minus 5 into age in years minus 161. So, TEE equals to REE into AF, which is study or population specific activity factor. The second method is predictive equation using fat-free mass, FFM. This method is commonly used in research studies that include measurement of body composition using the dual energy X-ray absorptiometry, DEXA technique. The method is high in cost due to the DEXA scan involved and has precision comparable to BMR predictive equations based on anthropometric data. So, REE equals to FFM in kg into 23.9 plus 372. TEE here equals to REE into AF, which means a study or population specific activity factor. The third method is resting metabolic rate measurement. RMR measurement is commonly done using an open circuit system involving use of a hood or canopy or mask based equipment, often referred to as a metabolic cart. The principle of indirect calorimetry is to measure the oxygen consumption and or carbon dioxide production and convert it to energy expenditure using the formulae. RMR measurement is very precise when compared to calorimetric results and poses moderate subject burden and cost. Use of standard protocol and trained staff yields accurate results that can even be used to estimate energy needs for chamber studies. TEE equals to measured RMR in kilocalories into AF, or study or population specific activity factor. The fourth method is room calorimetry. This is the most sophisticated form of the open circuit system that involves placing the subject inside a room or chamber of known volume. The measurement can range from a few hours to several days. Energy expenditure measured through this method is considered the gold standard in the field of nutrition and metabolism. This method is very expensive, highly precise, and has a high subject burden. So, TEE equals to the 24-hour energy expenditure measurement in the chamber room. Now, let's look at the activity factors that we just mentioned in the equations. Activity factors are also referred to as physical activity levels or PALS, PALS, and have a wide range based on the population being studied. The following table categorizes PALS based on lifestyle. For seated work with no option of moving around and little or no strenuous leisure activity, the PAL is 1.4 to 1.5. For seated work with discretion and requirement to move around but little or no strenuous leisure activity, it's 1.6 to 1.7. For standing work like housework, shop or being a shop assistant, it's 1.8 to 1.9. So, significant amounts of sport or strenuous leisure activity like 30 to 60 minutes 4 to 5 times per week, it's plus 0.3 as increment. Strenuous work or highly active leisure, for that the PAL is 2.0 to 2.4. The joint FAO WHO and UNU Expert Committee on Energy and Protein Requirements suggests the following activity levels based on the intensity of occupational work. For men, the values of light, moderate, and heavy activities are 0.55, 11.78, and 2.10 respectively. And for women, the values for light, moderate, and heavy are 1.56, 1.64, and 1.82 respectively. After studying the components of energy metabolism and their assessment methods, it may be possible to verify the existence of the various factors that may affect its determination. Yet, even the most sophisticated method cannot accurately reproduce the number and complexities of the activities performed by individuals daily. Also, since individuals, even from the same population, may have different expenditure due to the complexity of the multiple factors that affect it, so analysis of samples of individuals should be evaluated with caution and to avoid bias. Now let's come to the conclusion. Energy expenditure can be considered a process of energy production from combustion of energy substrates like carbohydrates, lipids, proteins, and alcohol, in which there is an oxygen consumption and carbon dioxide production. Energy expenditure is the sum of the basal metabolic rate, or BMR, which is the amount of energy expended while at rest at a neutral temperature and in the fasting state, the thermic effect of food, DEF, otherwise known as the dietary-induced thermogenesis, and the energy expended in the movement of all types or physical activity, PA. Energy is measured in terms of calories or joules. 1 calorie is equal to approximately 4.2 joules. And there are several methods to estimate energy needs, like predictive equations using anthropometric data or fat-free mass, resting metabolic rate measurement, and room calorimetry.